Yeah, so I'm Brendan. I'm representing a multidisciplinary team of engineers, chemists, material scientists, all working together in the Tyndall Institute to develop a wearable potentiostat system for sweat sensing and other applications. So Tyndall Institute is in Cork, down here in the south part of the island of Ireland, which is otherwise known as not Cork. It's a multidisciplinary research institute. It's the largest research institute in Ireland. 650 researchers, 54 different nationalities, significant amount of infrastructure invested by the Irish government in the development of ICT, microsystems, micronanoelectronics, theory modeling and design of materials, atomic modeling, photonics and wafer fabrication. And currently this is us here. This is our Tyndall Institute. And recently the Irish government has invested very significantly to build another 10,000 square meter site adjacent to us in terms of development of new and novel technology. So, and my time has just started, thank you. My area is, so I lead an embedded systems group of engineers called the Human-Centric Systems Cluster. And it's all about embedding technology into the world around us. So a lot of wearable electronic systems, looking at muscle activation, looking at inertial measurement unit, working with medical clinicians, looking at things like Parkinson's disease, through the integration of technology, sensors, machine learning algorithms into embedded systems, typically wearable or embedded in the environment that people are in. So the team focuses very much on electronics, flexible electronics. One of the thrusts of our activities is sustainable materials and recyclability. So we're looking at new and novel materials that are recyclable or sustainable in nature. We're developing antennas, rectennas, wireless power transfer systems for energy harvesting and for communications, and low power sensing, and then machine learning AI algorithms. Sorry. And that's what the talk about is today. So it's about a potentiostat-based system that we're using to integrate our novel sensors into the system design and the electronics behind the integration of those electronic systems, and then particularly the testing of the Lig-based sensors that we've developed in terms of our wearable sweat sensing devices and the microfluidic systems associated with that. So we're familiar with the PAM-Sense, Sensits, the research prototypes that many research institutes are developing to interface to wearable sensors and other different types of electrochemical sensors. But what we saw a need for was for multimodal sensing, for tracking of vital biomarkers, and a wearable low power consumption system to enable that. So we developed our own system. So it's based around a microcontroller core, typical embedded system. It's compatible with a wide variety of different types of sensors, and we're working with a number of partners internationally, looking at our Lig-based sensors, but also different biofet sensors and screen-printed electrode sensor systems. And I guess the reconfigurability of the system that we've developed makes it compatible with this wide variety of needs. So microcontroller, wireless communications, antenna, battery-powered systems, and then this reconfigurable electrochemical shield, which is what makes it special and compatible with all these different types of sensors. It's small in form factor, so this is the system we developed. It's designed to be worn on the body for sweat sensing. So where do people sweat? It's on their forehead, on their arm, or on their back. So it's a small form factor electronic-based system based around microcontroller core, the ESP32. It's highly available. It's very low cost. I mean, I guess one of the features of our system and the design requirements was that it would be a low cost system that's easily manufactured and easily used. And the significant amount of data sheets and documentation that's associated with the ESP32 makes it very compatible for people to use. And similarly, the electrochemical sensor interface gives us the ability then to look at multimodal sensing, integrate and sense concurrently different sensors at the real time. So as I say, the focus of this talk is primarily based on the Lig-based sensors that the team are developing, looking at glucose, lactate, and pH. using our system then for amperometry, cyclophotometry, and open circuit voltage testing to test those parameters for the systems that we've developed. We have a program in Tyndall called InfraChip, which gives us the ability to work with international partners. So in one project, we're working with our friends in Bhopal, and we've just finished a FET-based measurement integration of our system, and we've shipped our systems over to them so that now they can do wearable FET-based testing for using their sensors that they've developed. And similarly, we've just started with Tashkent University in India, a test program looking at SPE sensors. So in terms of laser-induced graphene, most of you are probably familiar with that, but basically we have the capability to do high precision deposition of different electrode tracks and use those tracks and functionalize them to test for different parameters in different fluidic systems. We're looking at sustainable materials, so polyimide and Kapton tape in the first instance, but we're also looking at materials, things like chitosan, which is a material that you get from shell crustaceans, shrimps, and is also from mushrooms. So we take this, those Lig-based structures, those electrodes, and we can then functionalize them to look at lactate, glucose, and other parameters of interest. And this is the work of Hassan Hamidi, and the details on the sensor development work that he's doing are in this publication here. So in similar work by our PhD student, Mohammed Rasel, he's looking at taking these sensors and working with Conor Manny to integrate those Lig-based sensor systems into applications such as wound care, smart bandages, smart diapers. He's looking at cortisol measurements, particularly for stress monitoring. And again, the system that we've developed in the front end gives him the capability to wirelessly measure the parameters that he's looking at in all these different types of applications. The microfluidics aspect is one thing that's quite an unsolved problem in terms of wearables. How do we get the sweat from people onto the active electrode and the active part of the sensor system? So we've developed a microfluidic system with multiple inputs. This is the active area here. And we've, through measurement, we've established that the reservoir fills every 98 seconds. You can see here tests with ferrocene over extended periods of time, where we're putting in different concentrations of ferrocene solution and seeing how the reservoir is reacting to those ferrocene concentrations. This microfluidic system that we have developed is solid. It's not flexible, but we are working on a flexible implementation of it. And of course, we have a smartphone application looking at the different parameters of interest, looking at double amperometry, single amperometry, cyclic voltammetry, and fast amperometry. And this is the wearable system on a fake person's arm to test for the microfluidic capabilities of the system that we've developed. So testing in the lab, so we've gone through the ferrocene analysis of the system to see how the electrochemical properties of the sensor work. Our gold standard is Autolab, a desktop-based system, and we're doing comparison then between the Autolab-based system and our potentiostat-based system to measure sweat glucose levels. Initially, with standard fluidic concentrations ranging from 0.2 to 0.01 to 0.2 millimolar, which is the typical sweat glucose range. And the limits of detection for the glucose sensor that we've developed are for about 14.9 micromolar. The glucose biosensor sensitivity is about 40 nanoamps per micromolar. And we have an accuracy of about plus or minus 10% based on glucose measurements. And this then is initially tested on the Autolab system, but again, correlated in our prototype system. And you can see the very close correlation between the gold standard testing and the prototype that we've developed, which is a far more mobile and wearable version of the potentiostat of the Autolab-based system that chemists typically use. So we've done that testing for single sensing. You can see here a dual biosensing platform looking at glucose and lactate. And you can see again the concurrent measurements of glucose and lactate at the same time in a very reproducible, selective, and stable manner over periods of hours and periods of weeks before the stability of the functionalization material starts to break down and the accuracy levels of the sensor start to degrade. And again, This is the work of Hassan and the publication associated with the description of this work and the detail on it. So we've developed a platform. We validated it against gold standard-based technologies, the Autolab, and we're now taking this system out of the lab and seeing can we measure human performance with it. So one of the areas that we're working at is to optimize the microfluidics of the system, make it flexible, and do actual sweat-based measurements out of the lab and on human trials that we've received ethics approval for. And the first stage of that then, of course, is testing on artificial sweat, looking at the different interfering parameters to see can we establish the levels of glucose and lactate within an artificial sweat type of compound material. And then test this with our sports scientists to correlate glucose and lactate levels. And what we're trying to do there is monitor, prevent injury, and promote return to wellness after post-injury. We're looking at improving the accuracy of this by incorporating multimodal measurements, such as pH and temperature, again, and doing data fusion to optimize the accuracy of the measurements for the glucose and lactate and other elements that we're interested in. And then our ultimate goal is to make this into a flexible wearable patch-based system and do an NFC or an RFID-based implementation to take away the clunky electronics that takes up a significant portion of this matchbox-sized device and integrate everything into a single patch without any battery. So the future work is integrating those multimodal smart algorithms and different IoT applications, not just in sweat, but also in animal health or in plant science. We're looking at integrating the electronics and sensors that we've developed onto some more sustainable materials. So I mentioned chitosan and polyimide, but we're also looking at textile-based electronic systems, integrating these types of sensors that are flexible and sustainable in nature. Our ultimate goal then is, as I say, to take this into a patch-based system, battery-free, RFID or NFC enabled to enable real-time testing on demand of the parameters of interest in the field by sports scientists. So thank you very much. If you have any questions.